Hello class, these are our notes for AP Calculus AB. Our section this time is 4.6 Numerical Integration. So I don't feel like numerical integration is really a very good descriptor. It's really all about the trapezoidal rule and then Simpson's rule. So let's go ahead and work on these two. Oh, there's my pen's working now. So trapezoidal rule, I really want to kind of sketch this out and we're going to be deriving it. So let's go ahead and make our X and Y axis. Here's some kind of shape. I'm making it very exaggeratedly curvy for our purposes here. And we're going to be integrating this from A to B. And I'm going to show dividing this into three different intervals here, or subintervals. So if we kind of just quickly review what trapezoids are. So let's look at area of a trapezoid. So trapezoid area is 1/2 height times base 1 plus base 2. So remember when we look at a trapezoid, this would be my height. It's going to connect my bases and my bases are parallel. The other thing that I want us to think about here is when I'm looking at this particular trapezoid, I've really got to think about how, well, let's go ahead and connect them first. So when I go to connect a trapezoid, I want to connect like this, right? And I'm kind of making this purposely off by a little bit. Let's try and make that trapezoid look a little bit better. So I can see that my two different heights are really like the base of the one I drew, the two parallel bases. And then the height would really be like this here along the bottom. So it's like the width of the interval. So here's my three different trapezoids. You can see one is a little bit under of an estimation. The other two are over. So that's what my area would look like with trapezoids. Okay, so next step here, if we're thinking about how to approximate this, I've got my two different bases. My bases would be those parallel. So like let's call this one base 1. This is going to be base 2 for my first trapezoid, and then for my middle trapezoid, I'd be using base 2 and base 3. For my third trapezoid, I'd be using base 3 and base 4. Okay, and I know this is a little bit weird because I have a B for my interval, and I've also got B1, B2, B3, B4, and maybe not really my interval, but my lower and upper bounds, I guess is what we could call that. So we're going to be approximating the area under that curve. So we're really looking at the integral from a to b of f of x dx. And when I think about adding these three different trapezoids, let's remember each trapezoid is going to have that 1/2. And then the way I would find my height here is my height is really the width of each interval. And the way I would figure that out is I would subtract b minus a, and then I would have to divide it by how many intervals we have. So I'm just going to make a note down here that we have n intervals. So each trapezoid is going to have a 1/2. It's going to have a b minus a over n. And then I'm going to have to add my two different bases. So for my first one, I've got base 1 and base 2. And then for my trapezoid, I still have the 1/2. I still have the b minus a over n. But now for my middle trapezoid for this one, my bases are b2 and b3. So what I want to point out right now is that second base, b2, I'm using it here and I'm using it here. So I'm using it in more than one place because it's part of two different trapezoids. For my last trapezoid, I would have 1/2. And then I would have b minus a over n. And I know you're thinking I could just put a 3 in there, but I'm trying to keep it a little bit more general. And then for my last trapezoid, I would have b3 plus b4. So again, I used b3 more than one time. So my ends of those trapezoids are of the function, like the b1 and the b4, I only have one time, but all my other letters in between, I'm going to be using multiple times. So the way I would simplify this is then at the very beginning, I could factor the 1/2 and the b minus a over n out of all of them. And then I would have b1 plus b2 plus another b2 plus b3 plus b3 plus b4. And then I want to make one more quick change. I'm going to put my fractions together and have b minus a over 2n. And then I would have b1 plus 2b2 plus 2b3 plus b4. So what I really want you to get out of this is that in my simplified version here, it's kind of exactly what we've got down here. I've got my 1/2, right? I've got my b minus a over n. That's the width of an interval. So this is 1/2 times my interval width that I have in front of this formula here. And when I'm looking at all of those different y values, my beginning and end y values, I use one time. And all of my middle y values, I use twice. So I have a 2 in front of them for a coefficient. So this only works if we have a bunch of the same interval width. And so what I find is, like in a practical application, if you're really approximating a function, we would absolutely want them to have the same interval width. But I find on AP stuff, this is usually going to be seen in the form of a table, and the interval widths will not be the same. So even though we're going to be using this formula in our math book, it's got a lot of practical applications that make sense. You're not really going to be using it on the AP test. So the difference for Simpson's rule, if you look at Simpson's rule down below here, for Simpson's rule, you can see in our fraction, instead of a b minus a over 2n, there's a 3n. So this one is really a 1/3 times the interval width. So still that b minus a over n. And then instead of a 1, 2, 2, 2, 2, 1 pattern, and let's note here that Simpson's rules for even numbers of intervals, I have a 1, 4, 2, 4. That pattern keeps repeating all the way until we get to a 4 and then a 1 again at the end. So Simpson's rule, basically what it's doing, and we're not going to do this derivation, is it's taking the trapezoid and then it's using like a polynomial thing to put a curvy top on it. So it's really a trapezoid with a curvy top, which is going to make it even more accurate. All right, so we are now going to go through and we're going to approximate the area under this curve. We're going to approximate this integral using the trapezoidal rule and Simpson's rule when n is 4. So the first step is I like to make a table. I don't want to have to plug into this function over and over again and keep rewriting 2x squared plus 1. So let's see, I want to go from 0 to 4, and n is 4. So if I think about my interval width will be 4 minus 0. Those are my upper and lower bounds. So that means the whole interval itself is 4, but I want to divide it into 4 parts. So each 1 unit will be my interval width. So that tells me how to build my table. So for my table then, I want to split it up every 1 unit. So I'm just going to write 0, 1, 2, 3, 4. And then I'm going to plug all of those y values into my, or all these x values into my function and get a y value. So 2 times 0 squared plus 1 is 1. 2 times 1 squared plus 1 is 3. 2 times 2 squared plus 1, 2 times 4 plus 1 would be a 9. This one's a 19. This one's a 33. So now essentially what we're going to do is we're going to think about building all of these different trapezoids, right? So like I would first have a trapezoid. If I look at these 2 entries in my table, my trapezoid would be 1 wide, and on one side my trapezoid would be 1, on the other side it's a 3. So I've got my 1 and my 3 as my y values, and then that x value, that 1, is basically my interval width. The next one, I would have a trapezoid with one side that's 3, but then the other side is going to be 9. So it'd be a lot taller on the other side. I've got all these trapezoids that I'm trying to find the area of, and then I'm going to be adding them all up. So that's essentially what we're doing. So don't be afraid to sketch this out if you're really lost. So I'm going to write the interval from 0 to 4 of 2x squared plus 1 dx is approximately equal to, first we're going to do trapezoid. So trapezoid says I use a 1/2 from the area of a trapezoid. And then I have that b minus a over n, which is just 1. And then I want to list out all of my different heights, all my y values. And remember, the first y value we're using 1 time. All of the middle ones we're using twice, because we have that shared side. So this is just that practical application of how do I use that formula to get an answer. So again, notice that when I write the 1 and the 33, those are my first and last y value. I use them one time, and the rest of them in the middle I am multiplying by 2 because it is a shared side. All right, then I want to go ahead and just multiply this out. So 1/2 times 1 is obviously just a half. When I add up all those values in the middle, I get 96. And half of 96 is going to be 48. So it looks like my pen is not working again. We'll try it maybe one more time, and then I'll just pause the video and restart it.